Hello, hello. Welcome back to our continuing of an introduction to drawing and naming alkanes. Now, guys, you've just been introduced in the previous podcast to the very beginnings of branching. But what happens if you have more than one branch on the same parent chain? That's going to change things a little bit. Now, key thing, super important. I write super important a lot in the notes this week. But if you have different branches present, more than one in other words, we list them in alphabetical order. And you can see from this name, that's how they're done. Now, the good news is a lot of times the names themselves give you hints as to what to do. Because if you forget how to draw it or how to name it, well, look back at another example that has a drawing or a name, and that can help you out. So notice that I've got a branch that starts with E, ethyl, and I've got a branch that starts with M, methyl. I have to write the E, ethyl first, and the M, methyl second. Why? Well, it's alphabetical, guys. So notice as well between every prefix, there is a dash for that and the number, okay? So pay close attention to the punctuation, if you will, of these names. Will I mark you wrong if punctuation dashes and we'll get to commas soon as wrong? 100%, I absolutely will. Because you are communicating in a language essentially that needs to be universally recognized. So you have to communicate properly. Alrighty, now this first time that we have a couple other branches, not just one coming off, the message remains the same. We're going to have our hex as our parent chain, so a 6-carbon parent chain. And we're also going to still be dealing with alkanes, single bonds. Now, in terms of our prefixes, our branches coming off, there's 2 of them. There's an ethyl, of course, and there's a methyl. Start drawing with your parent chain. That's always going to be your easiest route. 6 carbons. This one doesn't tell you if you have to draw a condensed structural diagram or a line, and so we'll do both so I can remind you how to do them, each of them. All right, so starting with the 6 carbons in the condensed. 1, 2, 3, 4, 5, 6. Don't draw your hydrogens in yet. The number of hydrogens is going to vary depending upon the branching. Think about the numbers. You can start from either direction, guys, from left to right, right to left. This time we'll start at the left. So carbon 1, carbon 2, and carbon 3 is our focus here. Now, there is an ethyl coming off of carbon 3. I'll draw that going down. So it's a CH2 and a CH3, right? A 2-carbon branch. I also have of a carbon 3 a methyl group. Methyl means 1, so it'll be a CH3 coming off of that. Okay, now we're finally where we can put our hydrogens on the other carbons. Starting from the left, we need 3 on this one. Now carbon's bonded 4 times. The second carbon, 2 more hydrogens to get it bonded 4 times. That third carbon, it's already bonded 4 times. Don't write any hydrogens on it. It's full. The 4th carbon needs 2 more, as does the 5th carbon, and our last carbon is a CH3. There it is, our structure of 3-ethyl, 3-methyl hexane. For a line structural diagram of the same one, focus on that parent chain first, 6. Now, as soon as your pen touches the paper, that's carbon 1. So carbon 1, 2, 3, 4, 5, 6, okay? Look in terms of counting and you can see that this worked out. 1, 2, 3, 4, 5, 6. Now we add our different side chains on. They both have to be on carbon 3, which is right here, okay? And you can draw both of them off of the same point. Our ethyl group is going to have a bend in it, and our methyl group is just singular. And you can see the carbons on those guys, right? Here's the 1 carbon on the methyl group. Here's the 1, 2 carbons on that ethyl group that have been added on. So we've got number 1, a condensed structural diagram. Number 2, a line structural diagram. Be able to be confident and familiar in both. Now, what if we've got a weird scenario like this one, where it's not 2 different branches, an ethyl and a methyl, for example, but we've got the exact same branch, multiple methyls or multiple ethyls, etc., etc. Another super important naming rule. If you have multiple occurrences of the exact same type of branch, we have to use another prefix. These are really familiar, guys. Di, tri, tetra. If it came down to it, penta, hexa, etc., etc. Okay, those are the same ones that we used when naming molecular compounds. Now, this is important though. Those prefixes are completely ignored when it comes to the alphabetical order. The alphabetical order is focused on the actual number of carbons, so the meth, eth, prop, bute, etc., etc. Okay? Now, just an example here of how this would work. Let's say we had two methyl groups, and we're going to have a long chain of carbons. There's one methyl group on carbon 3. There's a second methyl group on carbon 5. The way that we would walk through this is we would write the 3. Notice that it's separated with a comma. That's a new bit of punctuation that's being added in. 3, comma. Then we would write the 5. Now we're at the point where we need the dash. And then notice the di, stating that there are 2 methyl groups on there. Dimethyl. From an alphabet perspective, though, we would be alphabetizing them on the M, not on the D. Lots to take in. Let's look at an example in terms of the actual alphabetizing. Consider dipropyl versus ethyl. Don't look at the di. Focus on the P for propyl, the E for ethyl. Therefore, dipropyl would come after the ethyl, right? P is after E in the alphabet. Whew! Let's try a few. Okay. Name the following compounds. Lots to take in. Step 1, guys, figure out that parent chain. What is the longest length of carbons? Consider there's lots of ways to number these. And in many ways, sometimes it won't matter which one you use because you get the same answer. Let's imagine we go this way. 1, 2, 3, 4. Now, when I look at this one, I end up with the branches, and the branches here would be here and here, both of those coming off of carbon 3. That's what I get with my red numbers. Okay, let's do a different one. What if we draw them in green? Let's number out this one, and I'm going to go the other direction. So I can go this way. 1, 2, 3, 4. When I number that way, then I get my branches going here and here off of carbon 2. Ooh, that's better. Lower numbers. What if I ended up counting coming down from below? There's so many ways you can do this, guys. I'm going to clear that page so you can see my numbers again. So I'm going to this time go 1, 2, 3, 4. Oh, this works the same as what I just did in green. Here's a branch, here's a branch. Now, either way, 2 is the best way to do it. So let's go with this one. Like I said, if I'd kept it as the green numbers, that would have been just as good. Okay, so my parent chain that I can see there is going from here to here. That's my longest length, which gives me a bute. So let's start with that. And it's not just a bute, they're single carbon bonds, butane. Now I've got 2 methyl groups that I'd circled in blue there. So I know that I have dimethyl, 1, 2 of them. I see I'm going to kind of run out of room here. Let's see if I can write that better. Okay, here's my butane again that I just wrote. 2 methyl groups, dimethyl. There shouldn't be a space between the methyl and the butane. The last thing I have to do is state where they are. Both of those are on carbon number 2, right here. Okay, so you have to state it twice. It's on carbon 2, comma, there's another one on carbon 2, dash. Dimethyl butane. 2, 2, dimethyl butane. There's that di telling you there's 2 of them. Lots to take in, guys. I know that. All right, let's look at the second one. This is where it starts to get kind of wonky. Where is our longest chain? Whew. Okay, let's play around a bit. Here's one possible chain going like that. Let's see another one. Here's another possible chain going like this. I think any other variation isn't going to be any longer. Well, check out that yellow one. I've got 1, 2, 3, 4, 5, 6 carbons. If I check out that blue one, I've got 1, 2, 3, 4, 5, 6. Oh, so either one of those works out great. Now, which one, though, is going to give me my lowest numbers? Oh boy, here's where things get complicated. So we've already decided that no matter how I do this, I get 6 carbons. So that's good. Notice something else, whether I do the red numbers on the yellow or the blue numbers on the blue, I am regardless having a situation where I've got a branching off carbon 3 and branching off carbon 4. That didn't change. So picking the yellow or the blue, we get the same either way. I'm going to, for the sake of simplicity, go with this one here. Okay. Now, let's number these things again, and we've got 2 options for numbering. I'm going to put them both down. Our first option for numbering is going from left to right. 1, 2, 3, that puts 2 methyl groups on the 3. 4 puts an ethyl group on 4. 5, 6. So there's my red. The other option for numbering is going to be going the opposite direction. 1, 2, that puts an ethyl group on 3. 4 puts the 2 methyls on 4. 5, and 6. Alrighty, look through that. What's correct? Your goal here is to play with the alphabet rules. Either way, we get 3 is the lowest number. So that's good. And we can't change that. 3 and 4 is where the side chains are no matter which way we go. But and I'm going to name these both ways. So let's do the red way first. With the red way, we end up with, on carbon 4, an ethyl group. Okay, so 4-ethyl. And then we have on, with the red way, carbon 3, comma 3, 2 methyls, dash. So we write that as dimethyl. And then imagine I could keep writing beside. It's a 6-carbon chain, hexane. That's with my red numbering. 4-ethyl dash 3, 3 dimethyl hexane. Okay, let's look at the green numbering and see what we get. With the green numbering, we're going to end up with a 3-ethyl dash. Now the methyl groups are on the 4, 4, dash dimethyl hexane. Here's what's weird. They're not both considered right. Chemistry UPAC system dictates one of these is correct and one of them is wrong. And here's how we decide. When you look at the alphabet, E comes before M. E comes before M. In red, we have E going with the later number. And we have M going with the earlier number. That's not okay. This one's wrong. We need to have the E going with an earlier number and the M going with a later one. It gets complicated, guys. There's always rules to languages, and here's a new one for you. I have all that really outlined in the notes, please, so look back at it. Okay, here we go. Let's look at some drawings. Now, when you draw these, just kind of a step-by-step helpful thing for you, and I've been mentioning this already, draw that parent chain first. Then, after you've drawn the parent chain, attach the branches, which are the prefixes. Very, very last step is actually fill in the hydrogens. Otherwise, you could end up making a carbon bond more than 4 times, and we don't want that. It can only bond 4 times. How about this one? Draw a structure for 3-ethyl 2, 4 dimethyl pentane. Wow! Who knew you'd be able to do this, eh? Okay. Focus always on that parent chain first, right? Pentane. And we'll do these as both condensed structural diagrams and line structural diagrams. So honestly, before you even look at all those prefixes, let's just get that parent chain done. Pentane. Pent is 5. Leave spaces for hydrogens. 1, 2, 3, 4, 5. Okay, let's start putting the different side groups on. If I'm counting from left to right, then that would make this carbon number 3. Okay, so if that's carbon 3, that's where I'm going to put that ethyl group off of. And I'm going to draw this one down below. So it comes off. It's an ethyl group, so it has 2 carbons, 1, 2. And I'm putting those hydrogens on because I know that the side chains will have that many. Okay, so there's ethyl, 2 carbons, right? Ethyl, 2 carbons on carbon 3. Now it says on carbon 2, so imagine when you're counting carbon 1, this is carbon 2. On that carbon 2, I've got a methyl because it says on carbon 2, there's a methyl group. All right, let's draw it in. So off that carbon 2, a methyl group, I'm going to draw this one going below 2. You could draw it above, doesn't matter, CH3. I'm also told that there is another methyl group on carbon 4. So 1, 2, 3, there's carbon 4. Okay, so that carbon 4 is going to have another methyl group. I'm getting kind of squished below, so I'm going to draw this one above, CH3. There it is, 3-ethyl, 2,4-dimethyl pentane. Now, in terms of a line structural diagram, similar, focus on your parent chain first. Has 5. 1, 2, 3, 4, 5. There's our 5 carbons, right? Off of carbon 2 is a methyl group, 1 line down. Off of carbon 3 is an ethyl group. You're going to need to draw a skewed line, okay? Off of carbon 4 is another methyl group. Just to highlight, to clarify, there's carbon 1, 2, 3, 4, and 5. Here is my methyl group coming off of, I'll put that color on it, coming off of carbon 2. Here is an ethyl group coming off carbon 3. Here is a methyl group again coming off carbon 4, all right? Think about the numbers to help you. 1, 2, 3, 4, 5. And you can see then how those match. Off carbon 3, off carbon 2, off carbon 4. All right, folks. Hopefully this is starting to sink in. Let's look at the next one. 3,3,4 trimethylhexane. Tri because there are 3 methyl groups. Check out that parent chain, the root, hex. Okay, so let's start there with our condensed structural diagram. 1, 2, my pen doesn't work here. Let's try that again. There, go a little bigger. 1, 2, 3, 4, 5, 6 carbons. There's the hex. If you want to number them, if that makes your brain work better, feel free. Just don't get confused at the numbers mean, right? So here's carbon 1, 2, 3, 4, 5, 6. Off of carbon 3 twice, right? 1, 2. Off of carbon 3 twice is a methyl group. Methyl means a single carbon. So here's carbon 3 coming off here, and coming off here is a methyl group. CH3, CH3. Then coming off of carbon 4 is another methyl group. It doesn't matter if you draw it above or below. It means the same thing. CH3. There's my 3 methyl groups. Now I need to put my hydrogens in. 3 on the end, 2 for this one. Ooh, that 3rd carbon is already bonded 4 times. Leave it. The 4th carbon is bonded 3 times. I need 1 more hydrogen. 2 on the 5th one and 3 on the 6th. There is our 3,3,4 trimethylhexane. The line structural diagram. Parent chain is 6. So let's start drawing it. 1, 2, 3, 4, 5, 6. There they are. Off of carbon 3, I've got 1, 2 methyl groups. Off of carbon 4, 1 more methyl group. There it is. Count them. 1, 2, 3, 4, 5, 6. Right? There's your parent chain. Don't lose sight of where that is. Then the methyl groups are branched off. Alrighty, there is a good chunk of questions I want you to work on based upon those. It is these ones. Number 2, only A. You don't know how to do the cyclos yet. Number 3, AC, and number 4, A, B, C, and D. Now, guys, there is one more aspect to this, which is called physical properties of alkane. It's just a little chunk of notes. I'm going to talk about it quickly before we move on to cycloalkanes in the final podcast. We're just going to touch on this here. We do a lot more of it if we are in class. But a couple real good study points. Every alkane is nonpolar. Now, if you remember back to Chem 20, like dissolves like. So a nonpolar molecule can't actually dissolve in a polar substance, as in water, right? So alkanes are not soluble in water. They won't dissolve. Now, let's keep talking a little bit more about these alkanes. London dispersion forces, because it's nonpolar, are our focus here. So we're dealing with entirely an intermolecular force, which is all about size and shape, right? If you think back again to Chem 20. The size would be thinking about the molar mass. In other words, the number of electrons there too, right? So the bigger the molecule it is, the more electrons it has, the stronger the London dispersion force is. Also, the shape makes a difference. The longer it is, the more simply cylindrical that the shape is, it can have a lot higher London dispersion forces as well, which means, or intermolecular forces, right? Same. Which means that the bigger the molecule and the more cylindrical shape, the higher the melting point and boiling point. Okay, whereas the smaller the molecule, and honestly, the more spherical the shape, you're going to end up with a lower melting point and boiling point. You can see this. A really little one, methane, is a gas at room temperature, whereas you take quite a large molecule, octadecane, all of a sudden that one is a solid at room temperature. Pentane's in the middle, liquid at room temperature. Okay, now, in terms of having a definite way to do this, the small ones, specifically 1 carbon, 2 carbon, 3 carbon, or 4, will all be gases at room temperature. As this goes up, we end up with liquids, and liquids exist till about 8 carbons, and then as we get higher than that to the large molecules, we're up to solids. I already mentioned at the beginning, don't lose sight, they're nonpolar, therefore they are not soluble in water. Okay, like dissolves like. There's another question you can do that relates to physical properties, kind of, sort of. Number 6, in actuality, what this one does, guys, is brings us right back to the first unit where we were talking about combustion and about dealing with burning of things and how thermochemistry works into that. So for I wrote number 6. Oh yeah, that's one I wanted. Number 6. So for this one, guys, this goes into bomb calorimetry. Wow, back in time to stuff we did before the COVID-19 bizarreness that has happened. I really tried to give you some step-by-step hints on this question in the assignment. Use those to help you. I recognize you haven't done it in a while, so look back, look in the question, see the hints, the guiding parts of the question to help you along. All right, last podcast, final one of this week, will be on cyclohexanes. Talk to you later.